Hello there, and welcome to the Sleepy Science Channel. Tonight, we are drifting back through deep time, into the lost worlds that existed long before our own. Long before cities, before humans, before even familiar forests, the Earth was alive with ecosystems so strange and vast they almost feel imagined. There were seas filled with creatures unlike anything alive today. Forests without flowers, where towering plants spread in silence. Swamps where the air itself was different, and life grew in forms both immense and delicate. Entire landscapes rose, thrived, and disappeared, leaving only faint traces behind. These ancient ecosystems were not simple beginnings. They were rich, complex worlds, shaped by climate, chemistry, and the slow creativity of evolution. And each one tells a story about how life adapts, survives, and transforms the planet itself. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is settle in. Let your shoulders relax and notice your eyes grow heavy. And as the day begins to gently fade away, join me as we explore these ancient ecosystems together. Let's begin. Ancient ecosystems once grew forests where Antarctica now lies frozen. It is one of the strangest reversals in Earth's history. The coldest continent on the planet once held river valleys, dense woods, and long summer days that nourished living green worlds. In the age of dinosaurs, Antarctica was joined to other southern lands, and the climate was far warmer than it is now. There were conifer forests, fern-covered ground, and freshwater systems alive with insects and vertebrates. Even more astonishing, some of these ecosystems endured months of winter darkness each year. That means the plants and animals living there were not only surviving warmth, but also adapting to a rhythm of light and darkness, unlike anything in most modern forests. Fossils of leaves, wood, and tree rings show that these southern ecosystems were not sparse outposts. They were thriving habitats. It is a powerful reminder that Earth has changed so completely that even ice can hide a lost forested world. Before flowers existed, whole worlds were ruled by ferns and conifers. For a vast stretch of time, the Earth was green without looking anything like a modern meadow or garden. There were no roses, no grasses, no fruit trees, and no fields filled with blossoms. Instead, ancient landscapes were dominated by fern prairies, towering conifers, seed ferns, cycads, and strange plants with forms that now feel almost prehistoric in the imagination. These ecosystems fed giant herbivores, shaded riverbanks, and filled the air with spores rather than pollen from colorful blooms. The visual character of the world was completely different. Forest canopies were darker and more uniform, and the ground often carried thick layers of fronds and primitive undergrowth. When flowering plants finally began to spread much later, they did not enter an empty stage. They invaded an already rich planet and slowly changed its rhythms. Until then, entire ecosystems had thrived for millions of years without a single petal opening to the sun. Some ancient seas were packed with predators stranger than any dragon. Long before sharks became icons of marine danger, ancient oceans were already full of hunters that would look almost unreal to us now. In Cambrian seas, creatures like Anomalocaris swam through the water with grasping appendages, large compound eyes, and a circular mouth built for seizing prey. Later, oceans held armored fish with crushing jaws, squid-like cephalopods that could grow to immense lengths, and eurypterids that prowled estuaries like living weapons. These were not isolated monsters in an empty sea. They were part of crowded food webs where speed, armor, camouflage, and hard shells all mattered. Prey species burrowed, hid, clustered, and evolved defenses because danger was everywhere. That is what makes these ecosystems so gripping. They were not experimental sketches of life. They were already intense, competitive worlds filled with pursuit and escape. The sea was ancient, but it was never innocent. It had teeth, ambushes, and predators stranger than fantasy ever needed to invent. Giant insects thrived when Earth's air carried far more oxygen. There was a time when the air itself helped make the world feel oversized. During parts of the Carboniferous, oxygen levels were higher than they are today, and that mattered enormously for creatures that breathe through simple tube systems rather than efficient lungs. Insects and their relatives do not pump oxygen through bodies the way mammals do. They rely on diffusion, which places limits on size. But in an atmosphere richer in oxygen, those limits relaxed. As a result, dragonfly relatives could reach startling wingspans, and millipede-like arthropods could grow to lengths that seem almost unbelievable. Imagine wet forests, swampy ground, and the hum of wing beats from creatures that would look enormous beside a modern crow. These were not freak accidents. They were products of a planet whose chemistry opened doors that later closed again. When oxygen levels changed, so did the scale of life. Entire ecosystems responded, because even the air can shape what evolution dares to build. Reefs older than the dinosaurs were built by creatures now long vanished. When most people imagine ancient reefs, they picture coral and bright tropical fish. But some of Earth's oldest reef systems were built by communities that no longer exist in familiar form at all. Long before dinosaur-age coastlines, shallow seas hosted reef builders such as archaeocyathons, stromatoporoids, and tabulate or rugose corals. These organisms constructed vast limestone frameworks that sheltered other marine life, slowed waves, and created entire underwater neighborhoods. Reef ecosystems were already places of crowding, competition, and astonishing complexity. Small creatures found refuge in crevices. Grazers cropped surfaces. Predators patrolled edges where open water met stone. Some reefs rose for long periods, layer by layer, until they became massive living structures visible across broad seafloors. Today, many of those builders are extinct, and their worlds are gone with them. Yet their stony remains still survive in cliffs and mountain belts, reminding us that ancient seas once had their own bustling cities, built by hands evolution never used again. The first forests changed the planet by pulling carbon from the air. The arrival of forests was not just a local change in scenery. It was a planetary event. As trees and other large land plants spread, they began drawing huge amounts of carbon dioxide from the atmosphere through photosynthesis and locking much of that carbon into wood, roots, and buried organic matter. That altered the chemistry of the air and helped drive long-term climate shifts. But the transformation did not stop there. Roots broke into rock, accelerated weathering, and changed how nutrients moved across the land. Leaf litter began to accumulate. Shade appeared. Rivers slowed and branched differently as vegetation stabilized their banks. In other words, forests did not simply enter the Earth system. They rewired it. They created new habitats above ground and below it, while also helping cool the planet over immense timescales. It is astonishing to realize that the rise of trees was not only a biological story, it was one of the great atmospheric revolutions in Earth's history. Dinosaurs lived in ecosystems that included deserts, swamps, polar woods, and rivers. It is easy to imagine dinosaurs as creatures of one endless steaming jungle, but the truth is far more interesting. They occupied a huge range of environments across a changing planet. Some lived in dry dune fields where water was scarce, and survival depended on movement between precious wet places. Others moved through river valleys thick with vegetation, or across swampy lowlands where mud could trap footprints for millions of years. Some species lived in seasonal floodplains. Others endured polar forests with long periods of darkness. That range matters because it reveals dinosaurs not as a single kind of animal in a single kind of world, but as members of many different ecosystems, each with its own food webs, dangers, and rhythms. Their success came from flexibility. Different groups adapted to very different conditions and lifestyles. The dinosaur world was not one habitat scaled up. It was a patchwork planet, filled with distinct ecological dramas unfolding at once. Ancient food webs collapsed when volcanoes or asteroids changed the climate. Ancient ecosystems could appear vast and stable, yet some were more fragile than they seemed. When enormous volcanic eruptions darkened skies, released gases and disrupted temperatures, or when an asteroid struck with global consequences, the damage rippled far beyond the immediate event. Plants failed first in some places. In the oceans, plankton crashed. On land, food chains unraveled as herbivores lost dependable vegetation and predators lost prey. Rivers, coastlines, forests, and shallow seas all responded in different ways, but the pattern was the same. Once climate changed fast enough, complex systems began to break apart. What makes this so gripping is that extinction was not only about famous victims. It was about relationships being severed at every level. Pollinators lost plants. Scavengers lost carcasses. Young animals lost nursery habitats. Ancient ecosystems were networks, and catastrophe tore through the connections. What vanished was not just species, but entire living structures built over immense spans of time. Mammals once shared the night with dinosaurs in hidden ancient ecosystems. For much of the dinosaur age, mammals were present but easy to overlook. They were often small, secretive, and active in darkness, slipping through the underlayers of ecosystems dominated by much larger reptiles. Yet that hidden life was extraordinary in its own right. Early mammals and their close relatives burrowed, climbed, hunted insects, and searched for seeds or other food under cover of night. Some likely had fur, sensitive hearing, and warm bodies that helped them stay active when temperatures dropped. While giant dinosaurs controlled the daylight image of the age, mammals were exploring a different ecological opportunity. They took refuge in shadow, in dense vegetation, and in narrow spaces where size was a disadvantage. This matters because it turns the familiar story on its head. Mammals were not waiting for the dinosaur world to end before becoming interesting. They were already evolving clever ways to survive inside it, in ecosystems that were busy around the clock, not only by day. Some vanished ecosystems were so productive, they later became coal, oil, and gas. What we burn today often began as life in worlds so lush and active that they overwhelmed the normal pace of decay. In ancient swamps, deltas, shallow seas, and plankton-rich waters, huge amounts of organic material accumulated faster than it could be fully broken down. Layer after layer was buried by sediment, sealed away from oxygen, and slowly transformed over immense spans of time by pressure and heat. Coal often traces back to plant-rich wetlands and forests. Oil and gas commonly come from marine ecosystems crowded with microscopic life. That means some of the fuels powering modern civilization are compressed remnants of vanished worlds, built from leaves, wood, algae, and drifting organisms that lived hundreds of millions of years ago. It is a startling thought. Beneath our feet lie the concentrated remains of ancient productivity, preserved from sunlight and time. Entire ecosystems became geology and then energy, carrying the memory of lost life into the modern age. The Ediacaran sea floor hosted communities unlike anything alive on Earth today. If you could step into an Ediacaran seascape, you might not recognize much of it as animal life at all. The seafloor was covered with soft-bodied forms that looked like quilted leaves, rippled discs, fronds anchored to the mud, and flattened bodies with strange branching patterns. Many had no obvious mouths, eyes, limbs, or jaws. They seemed to have lived quietly on or within microbial mats that covered the sediment like living carpets. Some may have absorbed nutrients directly from the water. Others may have filtered tiny particles or grazed the surface in ways still debated. What makes these communities so captivating is that they feel less like ancestors of familiar ecosystems and more like a lost experiment in how life could be organized. Then, much of that world vanished. Later, ecosystems would be louder, faster, and more violent. The Ediacaran was different. It was a calm and alien chapter, where life covered the sea floor in forms unlike anything modern oceans have kept. Stromatolites built entire shallow ecosystems using microbes and sunlight alone. Long before forests, fish, or even simple animals reshaped the planet, shallow waters were dominated by structures built grain by microbial communities. Stromatolites formed when layers of sticky microbes trapped sediment, grew upward toward sunlight, and repeated the process over and over until they became domes, columns, and ridges rising from tidal flats. And lagoons. They look like stone, but their true makers were living films of tiny cells working together across immense stretches of time. These ecosystems mattered on a planetary scale. They helped shape coastlines, created habitat in otherwise simple shallows, and were part of the long transformation of Earth's atmosphere. In some places, they formed broad fields that would have changed water flow and offered surfaces for other microbes to inhabit. To imagine such a world is to imagine life before obvious drama. No roar, no chase, no footsteps. Only sunlight, water, chemistry, and countless invisible builders quietly raising whole living landscapes from the sea. Early reefs were once raised by archaeocyothans, not corals or fish. Some of the first reef builders on Earth would look unfamiliar even to a marine biologist. Archaeocyothans were small, cup-shaped animals that lived in early Cambrian seas, and for a brief but important window of time, they helped create reef frameworks in warm, shallow water. They grew alongside microbes and other simple organisms, binding sediment and building structure where there had once been open seafloor. These were not colorful coral gardens in the modern sense. They were older, stranger communities, with a different caste and a different feel. Yet the ecological role was already there. Raised stone provided shelter, slowed currents, trapped food, and created niches for many other organisms. That is the fascinating part. Reef life was already inventing architecture very early in the story of animals. Then, archaeocyothans disappeared, and later, reef systems were built by others. Their reign was short, but they helped establish one of nature's most powerful ideas, that life can reshape the sea by building upward. Cambrian seas held layered ecosystems with hunters, scavengers, grazers, and burrowers. The Cambrian is often described as an explosion of new body plans, but what makes it truly gripping is the ecological complexity that came with them. These seas were not simply filled with odd creatures drifting through evolution's first draft. They already contained layered communities with distinct roles. Some animals prowled the water column hunting prey. Others crept across the bottom scavenging scraps or grazing on microbial films. Burrowers tunneled into sediment, turning the seafloor from a quiet surface into a three-dimensional habitat filled with hidden life. That change mattered enormously. Once animals began digging, the chemistry of the seafloor shifted. Old microbial coverings were disturbed, and new opportunities opened for other species. In other words, the Cambrian was not only about strange anatomy. It was about ecosystems learning depth, movement, and competition. The ocean floor became a busy place of ambush, escape, recycling, and shelter. It was the beginning of a more restless Earth, where food webs grew sharper edges. Trilobites lived in ecosystems as varied as beaches, slopes, and deep seas. Trilobites are often treated as symbols of one ancient moment, but they were astonishingly versatile animals that spread into an enormous range of marine settings. Some lived in sunlit shallows near storm-washed coasts. Others moved across continental shelves, while certain forms occupied deeper, darker environments far from shore. Their bodies reveal this diversity. Some had large eyes suited to brighter waters. Others had reduced vision or specialized shapes that suggest burrowing, swimming, or crawling across soft sediment. They fed in different ways too, depending on where they lived and what food was available. That broad ecological reach helps explain why trilobites endured for such a long span of time. They were not one type of creature repeating the same life over and over. They were a whole evolutionary radiation of marine survivors, adapting to beaches, slopes, basins, and reef edges. When you hold a trilobite fossil in mind, you are not seeing a single world. You are glimpsing an entire library of vanished seascapes. Anomalocaris hunted through ancient waters before fish dominated the oceans. Before fish rose to real power in marine ecosystems, one of the most striking hunters in the sea was Anomalocaris. It moved through Cambrian waters with a flexible body, broad swimming lobes, huge compound eyes, and a pair of grasping front appendages that could seize prey with startling precision. For a long time, paleontologists even mistook its body parts for several different animals because the creature seemed too strange to belong together. That alone tells you how unusual it was. In life, it may have cruised above the seafloor, scanning for trilobites and other animals below. Its eyes suggest excellent vision, and its body was built for active movement rather than passive drifting. What makes it so memorable is that it represents a turning point. Predation was becoming more intense, and ecosystems were responding. Armor, speed, and defensive behavior all mattered more once hunters like this appeared. The sea was learning pursuit, and Anomalocaris was one of the earliest signs that life had become dangerous in motion. Some Ordovician seas teemed with squid-like predators longer than a bus. In the Ordovician, long before giant sharks or marine reptiles became famous, some of the biggest hunters in the sea were stray-shelled cephalopods. These animals were relatives of squids and octopuses, but instead of soft, flexible bodies alone, they carried long, conical shells that could reach astonishing lengths. Floating or cruising through ancient water columns, they must have looked like pale spears drifting upright through the sea, with tentacled heads poised below. They preyed on smaller marine animals and occupied a level of predatory authority that still feels dramatic today. Their success tells us how rich these seas had become. You do not get giant predators without plenty of food below them, and Ordovician oceans delivered that abundance. Shelly animals, trilobites, early reef life, and many other organisms supported these upper-level hunters. It is a thrilling thought. A world of shallow seas spread across continents, and through those waters moved creatures longer than a bus, ruling ecosystems with silent tentacles and patient buoyancy. The first land ecosystems were tiny, low, damp worlds, hugging bare rock. When life first began spreading across land, it did not arrive as sweeping forest or meadow. The earliest terrestrial ecosystems were modest, close to the ground, and tied tightly to moisture. Imagine rock surfaces, stream edges, mud, and thin crusts of life clinging to places that were periodically wet. Small plants and plant-like pioneers lacked deep roots, tall stems, and the towering architecture we now associate with land vegetation. There was little shade, almost no true soil in the modern sense, and no grand canopy overhead. Yet these low communities were revolutionary. They began capturing sunlight on land, trapping sediment, and altering the surface chemistry of continents. Tiny arthropods likely moved among them, feeding or scavenging in a world measured in inches rather than meters. What fascinates me most is their humility. The conquest of land did not begin with spectacle. It began with quiet persistence on bare rock. From these thin, damp worlds came every forest, field, and terrestrial food web that followed. Fungi may have helped the earliest plants survive on land. One of the most important alliances in Earth's history may have happened almost invisibly. The first plants venturing onto land faced enormous challenges. Water was harder to access, nutrients were locked in raw mineral surfaces, and the ground itself was a harsh place compared with shallow water. Fungi may have helped solve those problems. By forming intimate partnerships with early plants, fungal threads could extend far into cracks and sediment, gathering water and minerals that simple plant bodies could not reach alone. In return, the fungi received sugars produced by photosynthesis. It is a beautiful arrangement, and it may have been crucial for turning scattered pioneers into lasting terrestrial communities. Even today, many plants depend on fungal partners below ground, so this relationship appears to run deep in the history of land life. That means the greening of continents may never have been a solo achievement. It may have been a collaboration from the beginning, with one kingdom helping another take its first uncertain steps onto a world of stone and air. Ancient soils formed only after ecosystems learned to break rock apart. Soil seems ordinary because we live surrounded by it, but true soil is one of Earth's great ecological inventions. It had to be made. Early land surfaces were dominated by bare rock, loose sediment, and only the thinnest coatings of organic life. Over time, pioneering organisms began the slow work of transformation. Plants, fungi, microbes, and physical weathering attacked rock from different angles. Roots and fungal filaments entered cracks. Acids and biological processes released minerals. Dead material accumulated, mixed with sediment, and helped hold moisture. Gradually, a new medium emerged, one that could store nutrients, retain water, and support more complex communities. Once real soils began to develop, terrestrial ecosystems gained staying power. Larger plants could establish more reliably, and whole food webs could anchor themselves on land. This is one of those changes that can seem almost invisible in hindsight, yet everything depends on it. Before forests, farms, or grasslands, life had to invent dirt. And that invention changed the face of continents forever. The first forests created shade, leaf litter, and entirely new habitats. Once tall plants began gathering into true forests, the land surface changed in a way that would have felt almost magical to any earlier ecosystem. Suddenly, there was canopy. Light no longer struck the ground evenly. Shade created cooler, damper conditions beneath trunks and branches. Leaves and woody debris collected on the forest floor, building layers of litter that sheltered small organisms and fed decomposers. Moisture lingered longer. Vertical space appeared, opening new living zones from roots to crown. This meant the first forests were not simply bigger versions of older plant communities. They were deeper worlds, structured in layers and packed with fresh ecological opportunities. Arthropods could hide, feed, and move through this new complexity. Water runoff changed. Microclimates formed. Fallen trunks became habitat in their own right. It is hard to overstate how important that was. Forests turned land into a more intricate place, where life was no longer spread thin across open surfaces, but woven through darkness, height, decay, and shelter. Devonian rivers changed when roots began gripping banks and redirecting water. Before deep-rooted vegetation spread widely, rivers behaved very differently. Channels often shifted across broad sediment surfaces, and banks lacked the firm reinforcement that roots now provide in many landscapes. As plants evolved stronger root systems, they began binding riverbanks, stabilizing sediment, and forcing water into more defined paths. That changed how rivers branched, where they cut, and where they dropped their loads of mud and sand. Instead of wandering in the old way, many systems became more structured, with narrower channels and floodplains shaped by vegetation as much as by current. This is one of the most astonishing examples of life redesigning geology in real time. Plants were not merely adapting to rivers, they were engineering them. In doing so, they created new habitats along banks, in backwaters, and across floodplain mosaics that became richer and more persistent than before. A root seems so modest when you see one. Yet multiplied across landscapes, roots helped redraw the movement of water on continents. Ancient floodplains became richer once plants slowed erosion and trapped sediment. A floodplain without much vegetation is a more chaotic place. Water spreads, sediment moves quickly, and the surface can be stripped or buried with little resistance. As land plants became more widespread and complex, that began to change. Stems, roots, and growing plant cover slowed flowing water and encouraged fine sediment to settle. Organic matter accumulated. Moist patches lasted longer. Channels and ponds could persist in more varied arrangements. In practical terms, this meant floodplains became ecologically richer. Instead of being mostly open sediment surfaces repeatedly reset by water, they developed into patchy landscapes with more stable niches. Small pools, vegetated margins, and moist ground created room for arthropods, microbes, and early vertebrates to occupy different roles. This kind of enrichment is easy to miss because it sounds subtle, but its consequences were enormous. Once vegetation learned to catch and hold the land itself, floodplains became more than river leftovers. They became living mosaics where many kinds of life could linger, feed, hide, and evolve. The rise of trees transformed weather, rivers, and atmospheric carbon together. Trees did not change just one part of the Earth system. They changed several at once, and that is what makes their arrival so powerful. By pulling carbon dioxide from the air and locking much of it into wood and buried organic matter, they helped alter atmospheric chemistry over long spans of time. Their roots changed how rainwater moved through landscapes, which affected runoff, sediment transport, and the shape of river systems. Their canopies influenced evaporation and local moisture cycles, helping reshape weather patterns in the regions where forests spread. These effects were not isolated. They reinforced one another. A greener land surface could cool, stabilize, and restructure parts of the planet all at once. That is the true wonder here. Trees were not only impressive organisms, they became environmental forces. When trunks rose and forests expanded, they helped connect sky, land, and water in a new way. The Earth before trees and the Earth after them were recognizably different planets in how they breathed, drained, and stored carbon. Early forests had no birdsong, only wind, spores, and arthropods. Try to imagine a forest that looks ancient, because it sounds ancient too. There are trunks, fronds, shadows, damp ground, and filtered light, but no birds are calling from the canopy. No mammals rustle in the leaves. No flowering scents drift through the air. Instead, the soundscape is simpler and stranger. Wind moves through primitive foliage. Spores are released rather than petals opening. Arthropods crawl, buzz, scrape, and clatter in the litter and on bark. This matters because it reminds us that ancient ecosystems were not just earlier versions of our own. They had their own atmosphere, their own rhythm, and their own emotional texture. A Devonian or early Carboniferous forest would have felt both familiar and deeply uncanny. The forms of life were changing the land dramatically, yet the sensory world lacked so many things we now associate with woodland. It was a forest before birdsong, before blossom, before the modern chorus. And that makes it feel beautifully, almost hauntingly, distant. Some Devonian ecosystems ended in repeated crises linked to spreading forests. The spread of forests was one of life's great triumphs, but triumph can carry consequences. As deep-rooted plants expanded across continents in the Devonian, they accelerated weathering and altered how nutrients flowed from land into rivers and seas. In some cases, that may have driven repeated ecological disruption. Extra nutrients washed into marine environments, where blooms and changing chemistry could help strip oxygen from the water. Shallow seas, which had long supported rich communities, became dangerous places during these episodes. Reef systems suffered, and many marine organisms faced severe stress. This is one of the most fascinating lessons in ancient ecology. A major innovation on land may have contributed to crisis in the oceans. The success of one realm reshaped another. It shows how tightly connected Earth systems had already become. Forests did not merely stand where they grew. They changed distant habitats by altering the planet's chemical balance. Even in deep time, ecosystems were linked by invisible chains of cause and effect. Armored fish once dominated freshwater ecosystems before many tetrapods appeared. Before rivers and lakes became known for amphibians and later reptiles, many freshwater systems were ruled by heavily armored fish. Some of these animals wore bony plates across head and body, giving them an almost machine-like appearance, as though evolution had built tanks for murky water. Among them were formidable predators with powerful jaws, alongside smaller species filling other roles within lakes, channels, and wetlands. Their presence tells us that freshwater ecosystems had already become complex long before four-limbed vertebrates spread widely across the land. These waters were not simple holding places waiting for the next great transition. They were active arenas with hunters, prey, and ecological structure of their own. Armor likely helped some species survive intense competition and predation, while other adaptations suited different depths or feeding styles. When you picture these ancient waters, think not of gentle ponds, but of contested environments filled with strange fish built for attack and defense. Tetrapods would arrive later, but the drama had already begun. Lobe-finned fish lived in swamps that prepared life for land. Among the most important animals in Earth's history were fish living in shallow, changeable waters, where the boundary between land and water was already blurred. Lobe-finned fish had fleshy, muscular fins with internal bones that made them different from the ray-finned fish that dominate today. In swamps, floodplains, and oxygen-poor pools, those fins could help with maneuvering through vegetation, pushing along bottoms, or coping with unstable environments. Some of these fish also had air-breathing abilities or structures related to lungs, which would have been useful where water held little oxygen. That combination is what makes them so captivating. They were not trying to become land animals in any conscious sense, yet they carried features that later proved invaluable for life beyond the water. Their world mattered too. These were messy, plant-rich ecosystems shaped by drought, flood, stagnation, and shifting channels. In such places, versatility paid off. And from that versatility came one of evolution's greatest transitions. Ancient wetlands were nurseries for the first four-limbed vertebrates. The first vertebrates with limbs did not emerge onto dry ground as conquerors marching into a new realm. They came from wet, unstable environments where shallow water, mud, dense vegetation, and seasonal change created both difficulty and opportunity. Ancient wetlands offered exactly that. Channels dried and refilled. Pools became isolated. Flooded surfaces connected one habitat to another for a while, then pulled apart again. In these settings, having limbs with digits could help an animal prop itself up, navigate cluttered shallows, or move between patches of water when conditions turned harsh. That is why wetlands were so important. They were not side stages. They were training grounds. The animals living there still depended heavily on aquatic life, but their bodies were beginning to handle a world with gravity, obstacles, and air in a new way. When we imagine the first steps toward land, we should picture reeds, mud, stranded pools, and teeming wet margins. The doorway to terrestrial life was a wetland, not a desert shore. Some early land vertebrates still depended on waterlogged ecosystems to breed. Even after vertebrates began spending more time on land, many were still tied to soggy habitats for the most important part of life cycle, reproduction. Their eggs lacked the protective features that later allowed reptiles to breed far from standing water, so they remained dependent on ponds, marshes, river edges, or swampy ground where embryos would not try out. This created an ecological tension that is deeply fascinating. These animals were becoming more capable on land, yet their family future still pulled them back to waterlogged places. As a result, early terrestrial ecosystems were shaped by that dependence. Wet margins became gathering sites, nurseries, and seasonal strongholds where adults returned and young began life. It also meant drought could be catastrophic in ways that later land vertebrates were better able to avoid. In these creatures, we see transition made visible. They were not fully of one world or the other. They belonged to a threshold, living partly on land while still trusting water to begin the next generation. Carboniferous coal swamps were humid worlds of giant club mosses and horsetails. If you walked into a carboniferous coal swamp, the strangest thing might be how familiar and alien it felt at the same time. There were forests, standing water, dense greenery, and thick, damp air, yet the dominant plants were not modern trees. Giant club mosses rose like scaly pillars. Horsetails reached heights that now seem impossible for their living relatives. Fern-like plants crowded the understory, and the ground was soft with waterlogged debris. These were flat, steaming landscapes crossed by channels and ponds, where plant matter accumulated in great quantities and oxygen moved through a world rich in growth. The architecture of the swamp was different from any modern forest. Trunks had odd textures, crowns clustered high above, and many plants reproduced by spores rather than seeds. It was an ecosystem built on wet abundance. Beneath its still surface, it was one of the most productive botanical worlds Earth had ever seen, and its remains would shape the future in a way no swamp ever should. Dead wood once piled up because ecosystems had not fully learned decay. There was a time when forests could produce vast amounts of woody material faster than the living world could efficiently break it down. As tree-like plants spread and tough tissues rich in lignin became common, ecosystems faced a new challenge. Wood is hard to digest, and the organisms most capable of dismantling it completely had not yet become as effective or as widespread as they are now. That meant fallen trunks, branches, and plant debris could accumulate in waterlogged landscapes instead of vanishing quickly back into the cycle of life. Imagine forest floors and swamp margins layered with stubborn remains, not because life was inactive, but because the chemistry of wood had outpaced the biology of decay. This imbalance mattered enormously. It helped bury carbon on a huge scale and contributed to the formation of coal-bearing deposits. In a very real sense, forests were producing more resistant material than ecosystems could fully process, and the leftovers became part of the geological memory of the planet. Vast carboniferous forests locked away carbon that cooled the planet. Those immense carboniferous forests did more than fill wetlands with towering plants. They also changed the atmosphere by taking carbon dioxide from the air and storing it in trunks, roots, peat, and buried organic matter. Because so much plant material accumulated and escaped full decay, huge amounts of carbon were removed from the active surface system and sealed into sediments. Over the long spans of time, that drawdown helped reshape global climate. It is one of the great feedback stories in Earth history. Life altered the chemistry of the sky, and the sky answered back with cooling conditions and expanding ice in some regions. What makes this so arresting is the scale. These were not modest local woodlands nudging the weather. They were continental ecosystems powerful enough to influence planetary temperature. A forest can feel peaceful and still, yet in deep time, forests became engines of atmospheric change. The Carboniferous reminds us that leaves, trunks, and roots can be as consequential as volcanoes when enough of them cover the Earth. Dragonflies with huge wingspans patrolled swamp ecosystems above amphibian-filled waters. Picture a swamp under heavy heat, with still pools below and dense stands of strange plants rising from wet ground. Now imagine a shadow passing overhead from an insect with a wingspan so large it would stop you in your tracks. Dragonfly relatives of the Carboniferous and Permian were among the most dramatic flyers of their age, riding above waterlogged forests where amphibians crowded margins and channels. These were not decorative creatures fluttering above the scene. They were aerial predators, equipped with keen vision and the speed to seize smaller prey in flight. Their size gave ancient skies a character that modern wetlands no longer have. Over the dark water, they would have been part of the food web's upper layer, while below them lurked aquatic hunters and the early vertebrates that made these swamps so dynamic. It is a thrilling image because it makes the ecosystem feel alive in 3 dimensions. Life hunted in the water, on the ground, and in the air above the reeds. Millipedes once grew enormous in leaf-littered ecosystems rich with oxygen. On the floor of certain ancient forests, one of the most startling sights would not have been a predator at all, but a giant detritivore moving slowly through damp plant litter. Huge millipede relatives, far larger than any living species, crawled through ecosystems where oxygen levels were higher and plant debris was abundant. They were part of a world built on accumulation. Fallen material covered the ground, moisture lingered, and the breakdown of organic matter supported an entire hidden economy of decomposers and scavengers. These oversized arthropods likely fed on decaying vegetation, turning dead plant tissue into something the rest of the ecosystem could use again. That role makes them fascinating. They were not spectacular in the way a giant hunter is spectacular, yet they reveal how ancient ecosystems scaled up from the bottom as well as the top. Even the recyclers became impressive. In those forests, the quiet work of decay was not hidden in tiny corners. It moved through the litter in bodies large enough to command attention. Seed plants spread into drier habitats and changed ancient ecosystems again. Spores work well in wet conditions, but reproduction tied so closely to moisture places limits on where plants can truly dominate. Seed plants changed that equation. By packaging the next generation inside a more protected structure, they gained an enormous advantage in landscapes where water was seasonal, patchy, or unreliable. This allowed vegetation to spread more confidently into drier settings and helped transform ecosystems beyond swamps and permanently wet lowlands. Uplands, better drained floodplains, and more open interiors could now support plant communities with new resilience. That shift mattered for animals as well. New food sources appeared, new shelter patterns emerged, and the map of terrestrial life became broader and more diverse. The rise of seed plants was not only a botanical success story, it was a geographic one. Life on land no longer had to cling so tightly to constant wetness. Entire ecosystems began moving into spaces that had once been harder to occupy, and the shape of continents changed with them. Permian ecosystems linked deserts, uplands, river plains, and seasonal wetlands. By the Permian, the land was no longer a patchwork, dominated mainly by endlessly wet forests. It had become a more varied and connected world, with ecosystems spread across deserts, uplands, river systems, and wetlands that expanded or shrank with the seasons. This diversity created long ecological chains across entire landscapes. Water flowing from high ground fed channels below. Seasonal floods reworked plains. Animals moved between habitat types as conditions changed through the year. Plant communities had to cope with dryness, heat, and periodic abundance rather than constant saturation. The result was a terrestrial world that feels more recognizably modern in its complexity, though its cast of organisms was very different from today's. What fascinates me about the Permian is that it was a world of ecological contrast. Dry dunes could exist not far from productive river belts. Harshness and richness were neighbors. Life had expanded into a broader menu of environments, and the land now held systems that were linked by water, climate, and movement across space. Some Permian herbivores grazed in communities before dinosaurs even existed. Long before herds of duck-billed dinosaurs or horned giants crossed Cretaceous plains, earlier herbivores were already shaping plant communities in groups of their own. In the Permian, large plant-eating vertebrates fed across landscapes that included river margins, open floodplains, and seasonally dry ground. Some likely moved in loose associations or congregated where food and water allowed. Their feeding would have mattered enormously. When large herbivores crop vegetation, trample surfaces, and move nutrients through their bodies, they influence what plants thrive and what habitats remain open. That kind of ecological pressure did not begin with dinosaurs. It was already part of the terrestrial story. These older herbivores remind us that community-level plant consumption has deep roots in time. The land was being shaped by mouths and movement long before the dinosaur age. If you listen carefully to Permian ecosystems, you can already hear a familiar ecological rhythm beginning. The slow, powerful influence of large herbivores on the structure of the living landscape. Ancient dunes record ecosystems that survived in truly harsh inland deserts. A fossil dune may seem like pure geology, but it can hold the ghost of the whole ecosystem that endured where survival looked unlikely. Ancient inland deserts were brutal places, with loose sand, intense heat by day, scarce water, and little protection from the elements. Yet life found ways in. Tracks preserved on dune faces show animals moving across sand in search of food, shelter, or the next reliable water source. Burrows reveal that some survived by escaping underground. Certain plants and plant communities must have occupied wetter margins, ephemeral channels, or rare stable patches that anchored the broader system. What makes desert ecosystems so compelling is their discipline. Every movement matters. Every route between resources can decide survival. Even when fossils are sparse, dunes record presence through footprints, traces, and sediment patterns that hint at extraordinary resilience. These were not empty wastelands waiting for better climates. They were functioning ecosystems at the edge of possibility, where life endured with precision rather than abundance. The worst mass extinction nearly erased Earth's ecosystems in one blow. At the end of the Permian, life on Earth faced a catastrophe so severe that it is difficult to exaggerate. Marine ecosystems were devastated. Land communities collapsed. Entire food webs that had taken immense spans of time to assemble were broken apart. The likely causes involved enormous volcanic eruptions, climate disruption, ocean chemistry changes, and a chain of environmental stresses that reinforced one another until many systems simply failed. What makes this event especially haunting is that it was not a clean, selective pruning. It was a near dismantling of the living world. Reefs vanished. Predators disappeared. Stable communities unraveled into survival mode. It is the kind of moment that reveals how fragile complexity can be when the background conditions of the planet change fast enough and hard enough. When people call it the greatest mass extinction, they are naming something almost apocalyptic. The Earth did not lose just a few famous groups. It lost the fabric of ecosystems across sea and land, all at once. After the Permian collapse, ecosystems rebuilt from a radically thinned world. The world after the end Permian extinction was not immediately rich again. It was a battered planet where many ecological roles had been emptied, and surviving lineages inherited a strangely simplified Earth. Recovery took time, and the first rebuilt communities were often sparse, unstable, and unlike the intricate systems that had come before. In some places, a few hardy organisms dominated because there was so little competition left. That alone is a remarkable image. After the greatest ecological collapse in Earth history, the planet did not bounce back with instant diversity. It crawled forward through a long rebuilding. New food webs had to form. Vacant niches had to be filled. Habitats had to regain structure. Over time, entirely new groups would rise into opportunities created by the disaster. This is one of the most powerful lessons of deep time. Life can recover from devastation, but recovery is not a rewind. What comes back is often different from what was lost, because the world has changed and evolution starts again from survivors. Triassic landscapes mixed crocodile relatives, giant amphibians, and early dinosaurs. The Triassic can be surprising because it does not belong neatly to one famous animal group. It was a mixed world, a time when crocodile-line reptiles, giant amphibians, and early dinosaurs all shared the stage across river plains, lakes, forests, and dry interiors. In some habitats, broad-headed amphibian predators waited in water like living traps. On land, reptilian lineages were experimenting with many body plans and lifestyles. Some ran upright, some sprawled, some hunted, some browsed. The result was an ecosystem mosaic full of evolutionary competition and ecological uncertainty. No single dynasty had fully taken command yet. That is what makes the Triassic so fascinating. It feels like a world in negotiation. You can sense old survivors from before the Great Extinction living beside new contenders that would later redefine the planet. These landscapes were not just transitional in a dull sense. They were dramatic, crowded proving grounds, where entire branches of vertebrate history were competing for the future of the land. Some early dinosaur ecosystems were crowded with rivals, not dinosaur monopolies. We often imagine dinosaurs bursting onto the scene and instantly ruling everything in sight, but early on the story was far less straightforward. In many Triassic ecosystems, dinosaurs were only one group among several serious contenders. Crocodile-line reptiles included agile runners, armored forms, and predators that filled roles dinosaurs did not yet dominate. Other surviving lineages also held ground in the same landscapes. That meant dinosaurs had to compete within crowded ecological communities rather than inheriting an empty kingdom. Their later success becomes more impressive when you see it this way. They were not guaranteed winners from the start. They were one branch in a noisy, competitive experiment unfolding after catastrophe. Some habitats may have favored their posture, speed, or growth patterns, but those advantages had to matter in real ecosystems filled with rivals. The early dinosaur world was not a monopoly. It was a contest. That gives these ecosystems tension, because the future rulers of the Mesozoic were still earning their place among many other remarkable animals. Conifer forests helped support giant herbivores long before grasses evolved. When people picture great herds of huge plant-eaters, they often imagine grassy plains. But the largest herbivores of the dinosaur era lived long before grass became ecologically important on land. Their food came from very different plant worlds, especially conifer-dominated forests and other non-flowering vegetation. Needles, shoots, seed-bearing structures, ferns, and cycads helped power the enormous bodies of ancient herbivores. This means Mesozoic plant communities had to produce and distribute huge amounts of edible biomass without a single modern-style meadow in sight. In some places, the land would have looked forested, patchy, and vertically structured rather than open and grassy. Yet it still supported animals of extraordinary size. That fact makes the ecosystem feel even more astonishing. Giants did not wait for modern plants. They rose in a world of conifer canopies, fern-rich understories, and broad plant communities organized in unfamiliar ways. Long before grazing on grasslands became a major force, browsing and feeding in older vegetation had already built some of the heaviest land animals Earth would ever know. Ancient monsoons shaped entire ecosystems across the supercontinent Pangaea. When most of Earth's land was gathered into the supercontinent Pangaea, climate did not behave in the way it does across today's separated continents. The sheer size of that landmass helped generate powerful seasonal patterns, including monsoonal systems that delivered dramatic swings between wet and dry conditions in many regions. That seasonal pulse shaped rivers, floodplains, vegetation, and animal movement on an enormous scale. In wet periods, channels filled, ponds expanded, and plant growth surged. In dry times, water shrank back, resources tightened, and surviving often meant enduring scarcity. Ecosystems had to be built for rhythm, not constancy. This is what makes Pangaean monsoons so important. They were not background weather. They were ecological architects. They determined when animals bred, where they moved, and what plants could persist. Whole communities were arranged around timing. Imagine a continent breathing in seasons, with life rising and contracting to match. In such a world, survival belonged not only to the strongest, but to the best at living by the calendar of the sky. Polar Triassic ecosystems endured months of darkness every year. It is easy to think of ancient warm periods as uniform worlds without real seasonal challenge, but high-latitude Triassic ecosystems tell a more interesting story. In polar regions, life could experience extended periods of darkness, even when the overall climate was milder than today. That means plants and animals had to cope with an unusual combination: relative warmth compared with modern polar conditions, yet still a yearly cycle of light loss that shaped growth, behavior, and survival. Forests could thrive there, but they did so under a strange rhythm. Animals living in those habitats were not dealing with endless tropical conditions. They faced prolonged dim seasons that would have changed feeding and movement. This matters because it broadens our view of ancient ecosystems. Dinosaurs and their contemporaries were not only creatures of sun-soaked lowlands. Some lived far from the familiar image, in high-latitude worlds where light itself became seasonal pressure. Even in deep time, the poles could be demanding places, defined by darkness as much as temperature. The first pterosaurs hunted above ecosystems already rich with insects and reptiles. When pterosaurs first entered the skies, they did not rise above an empty world. They joined ecosystems that were already busy on the ground and alive with potential prey. Insects filled the air. Reptiles moved across shorelines, floodplains, and dry ground below. Small vertebrates scurried through vegetation and along water margins. Into that layered world came the first vertebrates to achieve powered flight, opening a new zone of predation and movement. What fascinates me is how quickly the sky became part of the ecosystem rather than simply the space above it. Once pterosaurs appeared, food webs gained a new dimension. Hunting could happen from above. Coastlines and inland waters could be searched from the air. Escape strategies on the ground now had to account for threats descending from overhead. The first pterosaurs were not isolated marvels of anatomy. They were ecological participants, using flight to exploit landscapes already rich with life, and in doing so, they changed how ancient ecosystems were connected. Jurassic ecosystems supported giants by spreading food through huge plant communities. The Jurassic did not produce giant herbivores by miracle. It produced them by sustaining vast, productive plant communities across broad landscapes for long periods of time. Sauropods and other large plant eaters required enormous amounts of food, and that demand could only be met in ecosystems where vegetation was widely available and renewed reliably enough to support repeated proteas. Browsing. Forests, fern-rich lowlands, conifer stands, and river-fed plant mosaics together created a landscape of distributed abundance. The key idea is spread. Food was not concentrated in a few tiny patches. It was woven across great areas, allowing large bodies to keep moving and keep feeding. This helps explain why Jurassic giants could become so large. They were products of ecosystems built to sustain scale. The land itself was organized in a way that made gigantism ecologically possible. When you imagine those animals, imagine the vegetation behind them too. Their size was not only a story of anatomy. It was a story of landscapes capable of feeding mountains that walked. Sauropods were ecosystem engineers that trampled paths and reshaped vegetation. A sauropod was not merely an enormous consumer moving through the environment. By virtue of size alone, it changed the environment around it. Repeated movement by massive herds or individuals could trample vegetation, open pathways through plant cover, and compact soft ground near water or along common travel routes. Feeding high and low across different plants may also have altered which species recovered fastest and which zones remained more open. In other words, these giants did not just live inside Jurassic ecosystems. They helped structure them. This is the same broad principle seen in modern elephants, though on an even more dramatic scale. Trails can become corridors. Broken plants can create opportunities for smaller animals. Disturbed patches can reset local growth. The landscape after a sauropod passed may not have looked the same as before. That idea makes these animals feel even more alive. They were not background monuments. They were moving forces, pressing their shape into vegetation and soil and quietly redesigning the habitats they depended on. Predators like Allosaurus lived in food webs, not isolated worlds of prey. It can be tempting to imagine a predator like Allosaurus as a lone icon, all teeth and muscle, existing mainly to dramatize the dinosaur age. But no predator makes sense outside the web that sustains it. An animal like this depended on the whole ecological structure below and around it, including plant communities that fed herbivores, scavengers that shared carcasses, smaller predators competing for different prey, and landscapes that shaped where encounters happened. Rivers, forests, open ground, and seasonal patterns would all influence the rhythm of hunting and survival. Even a top predator is constrained by community. If herbivores shift, the hunter must shift. If drought changes where water gathers, the food web tightens around those points. That is why ancient predators become more fascinating when placed back into ecosystem context. They were not monsters standing apart from the world. They were expressions of it. Every tooth, stride, and ambush belonged to a larger system of energy, risk, and interdependence spread across the Jurassic land. Jurassic seas held reefs, shell beds, plankton blooms, and giant marine reptiles. The Jurassic Ocean was not one endless blue emptiness. It was a patchwork of living zones, each with its own drama and abundance. In warm shallows, reefs rose with dense communities of sponges, corals, and shell-bearing animals packed into bright underwater architecture. Nearby, shell beds formed where generations of hard parts collected and created entire bottom habitats for smaller creatures to hide within. In the open water, plankton blooms fed drifting food chains that supported fish, cephalopods, and larger hunters. Then there were the marine reptiles, immense predators like plesiosaurs and plesiosaurs, moving through these systems with power that still feels cinematic. What makes the Jurassic Sea so compelling is its fullness. It was productive from surface to sea floor. Tiny, drifting organisms helped sustain giant hunters. Hard-built reef worlds stood beside broader expanses of open water. It was a living ocean of structure, motion, and scale, where beauty and danger were woven together in every depth. Some lagoon ecosystems preserved jellyfish, footprints, feathers, and raindrops together. Certain ancient lagoons were so still and so delicately layered that they could preserve moments that normally vanish at once. In these protected basins, soft mud received the lightest impressions and then sealed them away before waves or scavengers erased them. That is why some fossil deposits can hold an astonishing mixture of things, not only bones and shells, but jellyfish outlines, dinosaur or bird-like footprints, stray feathers, insect traces, and even the dimples left by falling rain. It is almost like discovering a lost afternoon from deep time. A shoreline creature walks across wet sediment. A storm passes over. A feather drifts down. Somewhere nearby, a jellyfish is stranded or settles to the bottom. Then, the whole surface is covered and kept. These deposits feel intimate in a way giant skeletons sometimes do not. They capture behavior, weather, and fragile presence. For a moment, the ecosystem stops being abstract. You can almost hear the water and feel the rain landing on the mud. Ancient plankton changed marine ecosystems while also altering global chemistry. It is easy to overlook plankton because they are small, drifting, and often invisible to the naked eye, yet they have repeatedly transformed both oceans and the planet itself. Certain groups that expanded through the Mesozoic and later did more than feed marine food webs. They also changed how carbon and nutrients moved through the sea. Tiny shell-making plankton pulled dissolved materials from seawater, built vast numbers of mineral skeletons, and then sank when they died, carrying matter downward into the deep ocean and sea floor. That process helped shape marine chemistry over immense spans of time. At the same time, they fed small animals, which fed larger ones, which supported the rich layering of open water ecosystems. In other words, these microscopic drifters were both biological fuel and geochemical force. That double role is what makes them so astonishing. An ecosystem can be changed from the bottom by organisms too small to notice, and the chemistry of the whole Earth can shift because countless tiny lives are drifting, blooming, and sinking through the sea. Cretaceous ecosystems were transformed when flowering plants began to spread. When flowering plants began spreading across Cretaceous landscapes, they did not simply add color to an already finished world. They changed the pace, texture, and opportunities within ecosystems on land. Flowers brought new reproductive strategies, faster turnover in some habitats, and different ways of interacting with insects and other animals. Fruits and seeds offered fresh food sources. More varied plant forms appeared in places where older vegetation had long dominated. Over time, this helped create richer understories, more seasonal pulses of food, and new ecological relationships that would reshape land life far beyond the dinosaur age. It is tempting to imagine a sudden floral revolution, but the deeper fascination is in the gradual takeover. These plant-centered ecosystems already filled with conifers, ferns, cycads, and dinosaurs then began rewriting the rules from within. By the end of the process, the land looked and functioned differently. The spread of flowers was not decoration. It was one of the great biological reorganizations of the ancient Earth. Insects and flowers started ancient partnerships that reshaped food webs. One of the most elegant revolutions in Earth history, began with attraction. As flowering plants spread, many insects found new rewards in nectar, pollen, and the chance to move between blossoms carrying grains that helped plants reproduce. This was not a simple one-sided arrangement. It became a deep partnership shaped by timing, color, scent, structure, and behavior. Flowers evolved ways to guide visitors. Insects evolved bodies and habits suited to finding and using floral resources. Once that relationship strengthened, ecosystems changed around it. Plant reproduction could become more targeted and efficient. Insect diversity expanded into new niches. Animals that ate those insects or fed on fruits and seeds produced in greater abundance were drawn into the consequences. That is why pollination is more than a detail of plant life. It is a force that ripples outward through whole communities. The beauty of it is that such grand ecological transformation began with very small encounters, an insect landing, a flower offering, and a world slowly reorganizing around that exchange. Some dinosaur ecosystems included forests bright with early blossoms and fruit. Not every dinosaur landscape was a dark world of conifers and ferns alone. By the Cretaceous, some forests had begun to include early flowering plants, whose blossoms and developing fruits added new colors, textures, and food sources to the understory and edges of woodland habitats. The result may have been more visually varied than many people imagine. Beneath older plant giants, patches of early angiosperms could brighten the ground layer and stream margins. Those plants would have attracted insects, and in turn those insects would have drawn small predators and other opportunists. Fruits and seeds opened yet more pathways for feeding. What fascinates me is the contrast. Giant dinosaurs still moved through these places, yet beneath them the ecosystem was becoming more recognizably modern in some of its details. A forest could hold towering reptilian bodies and also the beginnings of botanical relationships that now define much of our world. It was an ancient stage already preparing for the future, one blossom and one fruit at a time. Hadrosaurs flourished in ecosystems dense with seasonal plant growth. Hadrosaurs, the duck-billed dinosaurs, were among the great successes of the late Cretaceous, and their success makes more sense when you picture the environments they inhabited. Many lived in productive settings where plant growth surged seasonally, especially across floodplains, delta regions, and other landscapes renewed by water and sediment. These were places where fresh shoots, leaves, and varied vegetation could appear in abundance, then shift with changing conditions through the year. Hadrosaurs were well suited to that world. Their jaws and teeth formed powerful grinding systems, allowing them to process large amounts of plant matter with impressive efficiency. They seemed built not for rare feasts, but for sustained feeding in rich, dynamic habitats. That likely helped them gather in large groups and dominate many communities. They were not simply common dinosaurs by accident. They were specialists for abundance and motion. In ecosystems where the land kept renewing itself, they turned seasonal growth into one of the most successful herbivore lifestyles of the ancient world. Horned dinosaurs lived in herds that altered ancient landscapes by grazing. A herd of horned dinosaurs was more than a collection of impressive skulls moving through the Cretaceous. It was a landscape force. Animals like ceratopsians fed low, cropped vegetation and likely moved across the land in numbers large enough to affect what plants remained, what patches recovered, and which routes stayed open through repeated TZR use. When many large herbivores graze together, they do not simply remove food. They redistribute nutrients, trample ground, and create zones of disturbance that other organisms must respond to. That means their presence could help maintain certain kinds of vegetation while suppressing others. Their famous horns and frills make them visually unforgettable, but ecologically, their mouths and feet mattered just as much. They were participants in the shaping of habitat itself. Picture broad floodplains or woodland edges marked by repeated feeding, shifting open patches, and heavily used paths. In that sense, Herding horned dinosaurs were not passive residents of ancient ecosystems. They were active editors of the plant world around them. Tyrannosaurs depended on complex ecosystems filled with scavengers and smaller hunters. A tyrannosaur stands so large in the imagination that it can seem to occupy the whole ecosystem by itself. In reality, an apex predator of that scale depends on richness below. Large prey animals must be abundant enough to sustain it. Carcasses must attract scavengers. Smaller predators and opportunists must work the same landscape at different scales and speeds. In late Cretaceous ecosystems, tyrannosaurs were part of this broader structure, not the entire structure. Juveniles may even have filled different predatory roles than adults, adding another layer within the same lineage. Around them lived smaller theropods, mammals, insects, decomposers, and a whole plant base that supported herbivore populations. This is what makes the tyrannosaur world more fascinating than a simple image of one giant hunter. Every bite, chase, and death belonged to a living network. A carcass left behind would become an event. A shift in herbivore movement would echo upward. Even the king of predators was only possible because the ecosystem beneath it was busy, crowded, and finely connected. Tiny mammals found ecological opportunities beneath the feet of giant dinosaurs. For small mammals living in dinosaur-dominated worlds, size was not only a danger, it was also an opportunity. Beneath the feet of giant herbivores and predators lay a dense layer of ecological possibilities: seeds, insects, carrion scraps, burrows, sheltered root zones, fallen logs, and nighttime spaces where being small was an advantage. Many mammals were active when larger reptiles were less dominant, moving through leaf litter, climbing, digging, or foraging in hidden corners of the ecosystem. Their bodies were suited to this quieter layer of life. They could exploit food sources too minor or too concealed to matter to giants. They could disappear into cover quickly. They could build a living in the margins of a world shaped by larger animals. That is what makes them so compelling. They were not merely waiting for the dinosaurs to vanish. They were already clever participants in ancient ecosystems, using smallness as a strategy. The great dinosaur world had an underworld too, and mammals were learning how to master it. Some Cretaceous forests burned often, making fire part of the ecosystem. Fire is not only a modern ecological force. In some Cretaceous forests, it was already woven into the rhythm of life. Charcoal preserved in sediments shows that certain landscapes burned repeatedly, which means lightning, dry seasons, plant structure, and available fuel came together often enough to make fire an expected presence rather than a rare catastrophe. That changes how we should picture these forests. They were not always still, wet green worlds. Some were flammable systems where burning opened patches, cleared vegetation, and reset local habitats in ways that influenced what returned afterward. Plants that could recover quickly or exploit disturbed ground would gain opportunity. Animals would face both danger and renewal, as freshly opened spaces altered food and movement. Fire makes an ecosystem dynamic in a very particular way. It destroys, but it also rearranges. In the Cretaceous, some ancient forests were already living with that cycle. Even among dinosaurs and early flowers, flame was helping shape the structure of the land. Amber can trap whole microecosystems, including pollen, feathers, and parasites. Amber is often treated as a beautiful fossil medium, but its real wonder is that it can preserve not just individual organisms, but fragments of entire tiny ecosystems. Resin oozing from ancient trees could catch whatever happened to pass through or brush against it. Pollen grains drifted in. Tiny insect became trapped. Feather fragments, fungal threads, plant bits, mites, and even parasites riding larger hosts could all be sealed together in one golden drop. That means amber can capture relationships as well as bodies. It can show who was feeding on whom, what plants were present nearby, and which miniature worlds existed on bark, in leaf litter, or among forest canopies. The scale is small, but the insight is enormous. Amber lets us peer into the intimate life of ancient forests, not only the giants that walked below them. It preserves the overlooked layer, the buzzing, clinging, drifting, crawling layer that made the ecosystem feel alive from branch tip to tree trunk. Ancient termite and ant societies were already shaping soils before dinosaurs vanished. Long before the age of dinosaurs ended, social insects were already doing one of the most important ecological jobs on land. Termites and ants were reworking soil, moving particles, concentrating organic matter, opening tunnels, and changing how water and air moved below the surface. These activities may seem humble compared with the march of giant herbivores or the strike of famous predators, yet they are foundational. Soil structure affects roots, microbes, moisture, and the many small organisms that build the base of terrestrial ecosystems. Once insect societies begin engineering the ground at scale, the land itself behaves differently. That is what makes their early presence so fascinating. Beneath the visible drama of the Cretaceous, hidden labor was already transforming the substrate of life. Colonies were building worlds from below, chamber by chamber, and tunnel by tunnel. Dinosaurs dominated the skyline, but underfoot social insects were becoming powerful ecosystem shapers. Their work was quiet, collective, and easy to miss, yet it changed the very ground ancient life depended on. Mangrove-like coastal ecosystems existed long before modern shorelines looked familiar. The ancient coast was not always a simple line where land met sea. In some places, shallow edges hosted rooted plant communities that functioned much like modern mangroves, stabilizing muddy shorelines, trapping sediment, and creating tangled transitional habitats between beach air, fresh and salt water. These settings were ecological gold. They offered nursery grounds for smaller aquatic life, shelter from waves, and rich feeding opportunities for animals moving between land and water. Even if the exact plants were not modern mangroves, the ecosystem role was already emerging. That is what matters. Coastlines could become living filters, slowing water, capturing debris, and building intricate margins where many species interacted. Such places would have been full of movement, fish weaving through roots, invertebrates crowding soft sediment, and larger animals exploiting the concentration of life. It is astonishing how early this ecological idea appears. Before familiar modern shorelines took shape, ancient coasts had already discovered the power of rooted, muddy, sheltering edges where land and sea enriched one another. Inland seaways split continents and created rich coastal ecosystems full of life. At times in Earth history, rising seas flooded deep into continents and created vast inland seaways, turning single landmasses into separated regions with long new coastlines on either side. These were not lifeless channels. They became ecologically rich zones where shallow marine conditions, river inputs, and broad coastal margins combined to support remarkable abundance. Fish, sharks, turtles, marine reptiles, shell-bearing animals, and countless smaller organisms could thrive in these waters. Along the edges, deltas, estuaries, and coastal plains became productive habitats for both terrestrial and aquatic life. That is what makes inland seaways so exciting. They did not merely divide continents. They multiplied ecological boundaries, and boundaries are often where life flourishes. New migration routes formed. New nurseries appeared. Marine food webs pressed close to the land. A continent partially drowned became more, not less, biologically interesting. The shoreline expanded into the heart of the land, and with it came a broad ribbon of ecosystems where currents, sediment, and life met in extraordinary density. Mosasaurs ruled marine ecosystems that formed over drowned continental interiors. Mosasaurs feel like creatures of the open ocean, yet many of the seas they dominated spread across areas that had once been dry land. When continental interiors were flooded, broad, shallow marine systems formed where plains and lowlands had stood before. In these waters, mosasaurs rose to become some of the top predators, using powerful jaws, streamlined bodies, and strong tails to patrol ecosystems rich in fish, ammonites, birds, turtles, and other marine reptiles. There is something especially dramatic about that setting. These were not only ancient seas, they were seas laid across transformed continents, with new food webs built over drowned landscapes. Mosasaurs were the rulers of those reborn realms. Their presence tells us how quickly life can colonize opportunity when geography changes on a grand scale. A submerged interior does not remain empty for long. It becomes a hunting ground. And in the late Cretaceous, that hunting ground belonged in large part to mosasaurs, fierce swimmers made possible by seas that had swallowed the land. Ancient sharks thrived in ecosystems shared with turtles, ammonites, and giant fish. Ancient shark ecosystems were far more varied than a simple scene of one predator chasing one prey. In many Mesozoic seas, sharks lived alongside sea turtles, spiraled ammonites, bony fish of impressive size, and marine reptiles occupying other predatory roles. That means sharks were not solitary symbols of danger dominating a blank ocean. They were part of crowded and layered marine communities where many lineages overlapped in diet, habitat, and behavior. Some sharks specialized in speed, others in crushing hard prey, and still others in cruising broader waters. Their success came from flexibility within this busy ecological company. The presence of ammonites alone hints at the richness below, since such abundant shelled swimmers helped feed higher levels of the food web. Add turtles, schools of fish, and giant predators, and the sea becomes a world of constant negotiation. That is why ancient sharks are so compelling. They endured not by ruling a simple system, but by thriving inside complex marine webs already crowded with strange and powerful neighbors. Chalk seas were ecosystems built partly from countless drifting plankton shells. There were times when enormous deposits of soft white chalk began as the remains of tiny plankton drifting through ancient seas. Organisms such as coccolithophores produced minute calcium plates, and when countless generations lived and died, their remains settled to the sea floor in staggering quantities. Over time, that rain of microscopic shells accumulated into thick layers that would later harden into chalk. What makes this so mesmerizing is the scale mismatch. Vast seascapes and towering cliffs can trace their origin to lives so small they could fit beyond easy sight. Yet these drifters were not only geology in the making. While alive, they were part of marine food webs, helping support the layers of ocean life above them. So a chalk sea was both ecosystem and future rock, alive in the present and building stone for the future at the same time. It is one of Earth's most beautiful transformations, where drifting light-filled life becomes bright seafloor sediment and eventually the white bones of ancient landscapes. Deep ocean ecosystems existed even in ages we imagine as shallow seas. When we think of many ancient marine worlds, we often picture warm shallows, reef lagoons, and epicontinental seas spread across flooded land. Those environments were important, but they were not the whole ocean. Deep marine ecosystems existed alongside them, out beyond the familiar shallow settings, in darker waters where pressure, cold, and limited food shaped life in different ways. Sediments from deeper basins preserve traces of organisms adapted to those conditions, including communities that lived far below the bright zones most often shown in reconstructions. This matters because it reminds us that ancient oceans already had vertical complexity on a grand scale. The sea was not just a broad surface habitat. It was a layered planet within the planet, from coastal edge to abyssal depth. Even in periods famous for shallow inland waters, the deep ocean remained part of the story. It held its own rhythms, its own survivors, and its own hidden ecosystems, carrying on in darkness while the shallow seas captured most of the attention. Some fossil reefs preserve entire communities frozen where they lived. Few fossils feel more like a true ecosystem than a reef preserved in place. In some ancient reef deposits, organisms remain where they actually grew, sheltered, competed, and died. Framework builders still stand in relation to the cavities they created. Encrusting life clings to surfaces where it once spread. Small inhabitants remain tucked into crevices or scattered across the reef floor. Instead of a shuffled pile of remains, you get a community with its spatial logic still partly intact. That is what makes these reefs so extraordinary. They are closer to ecological snapshots than most fossils can ever be. You can read the neighborhood. You can sense who preferred shelter, who built upward, who exploited edges or overhangs. Preserved like this, a reef becomes more than evidence of species. It becomes evidence of living arrangement. Ancient ecosystems rarely stay assembled for us. Usually time takes them apart. But some reefs resist that loss, allowing us to glimpse not just who was there, but how they shared a crowded underwater world. Ancient cave ecosystems sheltered bats, insects, and predators deep in darkness. A cave is not just an empty hole in rock. It can be an ecosystem built around darkness, stillness, and whatever life manages to enter from the world above. In ancient caves, bats may have roosted in thick clusters, filling chambers with sound, movement, and nutrient-rich guano that fed insects, fungi, and whole chains of small scavengers. That alone could sustain an entire hidden community far from sunlight. Predators sometimes entered too, drawn by the concentration of prey or by the shelter itself. Bones in cave deposits can record a strange mixture of residents, visitors, and hunters, all brought together in a place where ordinary landscape rules no longer apply. What makes cave ecosystems so gripping is their contrast. Outside, weather, seasons, and daylight shape life. Inside, time feels slower. Temperature holds steady. Sound carries differently. Ancient caves remind us that ecosystems do not need sunlit grandeur to be rich. Sometimes they thrive in silence, under stone, where darkness becomes the organizing force. Lakes can preserve vanished ecosystems more delicately than rivers ever could. A river is restless. It drags, scrapes, stirs, and scatters whatever falls into it. A lake can be very different. In the right conditions, a quiet lake bottom becomes one of the gentlest archives on Earth. Fine sediment settles softly through still water and covers leaves, insects, fish, feathers, and pollen before currents can tear them apart. Layer after layer builds a calmer kind of fossil record, one that often preserves far more than bones alone. Whole seasonal histories can be held there. A leaf can fall from shore vegetation, an insect can land on the surface, a fish can sink below, and each may be sealed into mud with astonishing delicacy. That is why lake deposits can reveal entire vanished ecosystems with rare intimacy. They do not merely tell us who lived there. They show us weather cycles, shoreline communities, and subtle ecological detail. Compared with rivers, lakes can behave like memory itself, quiet, patient, and unexpectedly faithful to the small things. Fossil pollen can reveal an ecosystem long after its trees are gone. A forest can vanish completely from the surface, its trunks rotted, its roots erased, its animals scattered into time, yet one of its clearest signatures may remain in something almost impossibly small. Pollen grains are tough, abundant, and often beautifully distinctive under magnification. Different plants make different shapes, textures, and patterns, which means ancient sediments filled with pollen can reveal the character of a landscape long after the visible vegetation is lost. A mud layer may tell us whether a region held conifer woodland, fern-rich wetland, open shrubland, or an expanding wave of flowering plants. It can even show change through time as climates shift and ecosystems reorganize. That is what makes pollen so magical in paleontology. It turns dust into evidence. A whole vanished world can be reconstructed from grains light enough to drift on the wind. The trees themselves may be gone, but their reproductive traces linger like whispers, still able to tell us what kind of ecosystem once breathed there. Coprolites preserve ecosystem clues by recording ancient meals in detail. Few fossils feel less glamorous at first glance than ancient droppings, yet few reveal ecology more directly. A coprolite is a preserved piece of waste, and inside it can be an entire story of diet, behavior, and environment. Bone fragments may show that a predator chewed hard and swallowed deep. Plant tissue can reveal what herbivores were cropping in a particular season or habitat. Scales, shells, insect parts, spores, and even signs of parasites can all survive inside, giving us a direct glimpse of feeding relationships that skeletons alone could never provide. This is what makes them so unexpectedly thrilling. They record an ecosystem from the inside out. Instead of guessing who ate what, we sometimes get evidence carried straight through a body and fossilized at the end of the process. It is intimate, slightly strange, and scientifically powerful. In ancient ecosystems, even waste was part of the story, and sometimes it preserves the most honest record of a meal ever found. Tooth marks on bone expose predator networks inside vanished ecosystems. A skeleton can tell us who lived in an ancient world, but damaged bone can tell us how life and death moved through it. Tooth marks, punctures, scrapes, and bite fractures preserve moments of violence, scavenging, and competition that would otherwise vanish. A bone gnawed after death speaks differently from one bitten during struggle. Repeated marks from different jaw shapes can suggest more than one consumer working the same carcass. That is where things become fascinating. A single fossil may reveal not only one predator and one prey, but a whole network of opportunists arriving in sequence. Large hunters may have made the first kill. Smaller scavengers may have followed. Bone-cracking feeders may have taken what remained. Ancient ecosystems were not clean stories with one dramatic ending. They were crowded systems where death spread energy outward through many mouths. Tooth marks let us watch that transfer happen. They turn still bone into evidence of interaction, showing the predator worlds were shared, layered, and far more social than a solitary hunt suggests. Trackways reveal ecosystems in motion, not just skeletons after death. Bones usually tell us where an animal ended. Footprints tell us what it was doing while alive. That difference is extraordinary. A trackway can show a herd moving together, a predator changing direction, a small animal crossing mud between larger tracks, or a shoreline alive with repeated comings and goings. It preserves motion, spacing, hesitation, and sometimes even speed. In one moment of soft ground, an ecosystem can write itself down as behavior rather than anatomy. That is why track sites feel so immediate. They are not graveyards. They are living surfaces briefly turned to stone. You can sense weather, substrate, water level, and the rhythm of movement across the land. Sometimes many species used the same area within hours or days of one another, leaving overlapping evidence of coexistence that skeletons would never arrange so clearly. Ancient ecosystems become vivid when tracks appear, Because for once, the past is not only about who was there. It is about who passed by, where they went, and what the ground witnessed. Burrows show that ancient ecosystems extended underground as well as above. It is easy to picture ancient ecosystems as things that happened on surfaces, across plains, through forests, and over shorelines. Burrows remind us that a great deal of life happened out of sight. Tunnels in sediment preserve evidence of animals digging for shelter, raising young, escaping heat, hiding from predators, or waiting out drought underground. Some are simple hollows. Others are elaborate branching systems that suggest long-term occupation and careful engineering. This matters because it reveals an entire hidden layer of ecological strategy. The ground was not just something animals walked on. It was habitat in itself. A burrow can tell us about the moisture of the soil, the firmness of the sediment, the climate pressures above, and the behavior of the creature that made it. In harsh or seasonal environments, underground life may have been the key to survival. Ancient ecosystems were therefore deeper than they first appear. Beneath the visible drama of plants and large animals, a quieter architecture of tunnels helped many species endure. Ancient dung beetles helped recycle waste inside long-lost ecosystems. Even in the age of giant herbivores and strange vanished mammals, waste did not simply pile up untouched. Ancient dung beetles and similar recyclers were already turning animal droppings into ecological opportunity. By burying, rolling, and consuming dung, they helped return nutrients to the soil, reduce the spread of waste across the surface, and create feeding chances for their own young. That quiet work may not sound dramatic beside a charging dinosaur or a stalking predator, yet it is one of the most essential rhythms in any functioning ecosystem. Large herbivores produce abundance, and something has to process what they leave behind. Dung beetles do exactly that. Their activity links plant eaters back to the soil, which then helps feed plants again. In deep time, this made them part of the machinery that kept ecosystems cycling. What I love about that is the scale of the contrast. Vast landscapes and giant bodies depended in part on small insects doing dirty work with astonishing efficiency. Ancient worlds stayed alive because nothing went unused for long. Parasites lived in ancient ecosystems too, shaping survival in hidden ways. When we imagine ancient ecosystems, we tend to picture the visible actors, predators, herbivores, forests, reefs, and swarms of insects. Yet some of the most powerful ecological influences were probably invisible to casual view. Parasites lived in those worlds too, feeding on blood, tissue, or nutrients inside bodies much larger than their own. They may have weakened individuals, spread between hosts, altered behavior, and influenced which animals survived long enough to breed. A bite, a worm, or a blood-feeding arthropod could quietly change the outcome of a life. That is what makes parasites so important to remember. They add a hidden layer of pressure to ecosystems already crowded with visible danger. Survival was never only about avoiding teeth and claws. It also meant enduring the small lives that lived on or within larger ones. Fossils occasionally preserve evidence of these relationships through damaged bones, trapped insects, or exceptional preservation. When they do, they reveal a truth that feels deeply modern. Even ancient ecosystems were shaped by unseen struggles unfolding inside the body. Feathered dinosaurs belonged to ecosystems already experimenting with insulation and display. Feathers did not suddenly appear only to make flight possible. In many dinosaur ecosystems, feather-like coverings and true feathers were already serving other purposes, helping bodies conserve heat, signal to rivals or mates, and perhaps protect eggs or young. That means certain ancient landscapes were filled with animals experimenting in public with color, texture, and thermal control, long before birds fully took to the skies. Some small predators may have flashed patterned plumage in display. Others may have relied on fuzzy coats to stay active in cooler conditions. What fascinates me most is the ecological setting of that experimentation. These animals were not odd side branches isolated from the rest of the ecosystem. They were integrated hunters, foragers, and prey species living among plants, insects, and larger dinosaurs, while evolution tested new body coverings on the move. Feathers were part of an ecosystem conversation about warmth, visibility, and behavior. Before they transformed the skies, they were already changing how ancient animals looked, lived, and communicated on the ground. Polar dinosaur ecosystems may have faced frost, snow, and winter scarcity. Some dinosaur habitats lay so far from the equator that long, dark winters would have shaped life in serious ways. Even when the global climate was warmer than today, those high-latitude ecosystems may still have experienced frost, seasonal snow, and times when food became scarce. That means certain dinosaurs were not simply giant reptiles in endless warmth. They were animals coping with difficult annual cycles, low winter light, and periods when vegetation was less available. Smaller species may have hidden, huddled, or altered behavior seasonally. Larger herbivores may have depended on stored energy or on whatever plant material remained accessible through cold months. Predators would have felt those pressures too, because hungry prey changes the whole food web. This makes polar dinosaur ecosystems especially compelling. They stretch our imagination beyond the usual tropical image of the Mesozoic. Dinosaurs were adaptable enough to live where the year itself became a challenge, in places where survival may have depended as much on endurance as on size or strength. Antarctic forests once hosted dinosaurs beside rivers lined with conifers. It is one thing to know that Antarctica was once warmer. It is another to imagine dinosaurs moving through forests there beside flowing rivers lined with conifers and thick plant growth. Fossils from those ancient southern landscapes reveal a continent that looked nothing like the frozen desert we know today. There were wooded floodplains, soils, seasonal water systems, and animal communities able to live far within the polar circle. What makes this scene so powerful is the contrast with the modern continent. Today we picture ice shelves, blizzards, and barren expanses. Deep in time, the same land held green ecosystems and vertebrate life moving through them. The rivers mattered too. They organized the landscape, nourished vegetation, and created corridors of habitat through the forest. Antarctica was not a marginal outpost. It was part of the living world in full ecological detail. That reversal makes it one of the most astonishing reminders that Earth does not simply age. It reinvents whole continents beyond recognition. Madagascar preserved isolated ecosystems where evolution followed unusual ancient paths. When a landmass becomes isolated for long enough, evolution begins to improvise in its own accent. Madagascar is one of the great examples, and its ancient ecosystems show that this uniqueness runs deep in time. Separation from other regions allowed lineages there to follow unusual paths, producing communities that did not simply mirror those on nearby continents. Predators, herbivores, and smaller species could evolve in combinations that feel slightly offbeat compared with mainland expectations. That is exactly what makes such ecosystems so fascinating. Isolation changes the rules. Competition shifts. Chance matters more. A group that would remain minor elsewhere can become important. A familiar role may be filled by an unfamiliar kind of animal. In deep time, Madagascar was already preserving this kind of ecological individuality. Its landscapes became workshops for separate evolutionary experiments, shaped by distance and time. When we look at ancient island or Arabichin, Arabicba, Arabica island worlds like this, we see how geography can act like a composer, producing ecosystems with the same basic notes of life, but arranging them into completely different music. island ecosystems in deep time often produced strange giants and dwarfs. Islands are famous for making evolution behave in surprising ways. In limited spaces with unusual resource pressures and altered predator communities, large animals may shrink and small animals may grow far beyond their mainland relatives. This pattern, known from many times in Earth history, creates ecosystems that feel almost dreamlike. Dwarf herbivores can browse in habitats where giant bodies would be too costly. Small creatures freed from certain predators may become enormous. The result is an island world where scale itself has been rewritten. What makes this so exciting is that it is not random eccentricity. It is ecology made visible through body size. Every giant and dwarf is evidence of resources, isolation, competition, and opportunity acting together over long periods. Ancient islands therefore become natural experiments in how ecosystems reshape life. They show that the same lineages can produce radically different outcomes when geography changes the terms of survival. In deep time, many islands were not miniature versions of continents. They were evolutionary theaters where size became one of the boldest surprises. Some ancient ecosystems were dominated more by seasonality than by warmth. When people imagine deep time climates, they often focus on overall warmth or cold. Yet for many ecosystems, the most important factor may have been seasonality, the repeated swing between wet and dry, light and dark, abundance and stress. An environment can be warm on average and still be demanding if food vanishes for part of the year or if water arrives only in pulses. Ancient ecosystems shaped by these rhythms would have felt less like stable paradises and more like timed challenges. Plants had to grow when conditions allowed and endure the off-season. Animals had to breed, migrate, store energy, or change behavior to survive recurring bottlenecks. That creates a different kind of ecological drama. The question is not simply whether a habitat was warm enough for life, but how life endured the calendar it lived under. This matters because it makes ancient worlds feel more dynamic and more believable. Their defining pressure was often not temperature alone, but the repeated beat of seasons deciding when the ecosystem could truly come alive. Glacial intervals repeatedly squeezed and reshaped ecosystems across whole continents. Ice ages do not simply add cold to a landscape. They rearrange life across enormous distances. As glaciers expand, climates dry or cool, sea levels fall, habitats shift, and entire ecosystems are pushed, split, or compressed into smaller refuges. When the ice retreats, those communities expand again, mingle with new neighbors, or reorganize into different forms. Across continents, this repeated squeezing and release reshapes food webs, migration routes, and patterns of survival. What makes glacial intervals so fascinating is their rhythm. They do not just destroy. They force ecosystems to move, adapt, fragment, and reconnect again and again. Forests withdraw. Grasslands spread. Rivers change course. Animals follow the changing edges of suitable habitat. Over time, this can influence evolution itself by isolating populations and then bringing them back together. Ancient ecosystems under glacial pressure were therefore not static scenes of cold misery. They were mobile worlds, repeatedly compressed by ice and then reassembled, each cycle leaving a new imprint on the living map. After dinosaurs disappeared, mammal ecosystems rapidly explored newly opened roles. The end of the Nanavian dinosaurs did not leave a planet emptied of life. It left a planet full of vacant ecological roles. Mammals, many of which had long lived in smaller or more hidden ways, began expanding into those opportunities with remarkable speed. Different lineages explored life as larger herbivores, active predators, climbers, runners, burrowers, and eventually marine specialists. What is so gripping about this moment is that it was not simply a matter of mammals getting bigger. Entire ecosystems were being reorganized around new bodies, new feeding strategies, and new ways of using space. Forest canopies, open ground, riverbanks, and coastal margins all became stages for mammalian experimentation. The transition feels almost like an ecological release of pressure. For a long time, many mammals had lived beneath the dominance of larger reptilian rulers. Then suddenly, the landscape opened. The result was not one new order, but a burst of ecological invention. Mammal ecosystems began writing a fresh chapter by occupying roles that had once belonged to others. Ancient rainforests recovered slowly after the asteroid impact changed everything. The asteroid impact at the end of the Cretaceous did not only kill animals. It shattered plant communities too, and rainforests were among the ecosystems that had to rebuild from devastation. The loss of large dinosaurs, widespread fires, darkness, cooling, and disrupted growing conditions all changed the structure of tropical forests. Recovery was not instant. It took long spans of time for rich, layered rainforest systems to become established again in their new form. That slow rebuilding matters because it shows that forests are not merely collections of trees. They are architectures of interaction, canopy, shade, soil life, and food webs that require time to assemble. After the impact, plant composition shifted, and the rainforest that later emerged was not simply the old one restored. It was a transformed system. That is one of the most haunting things about mass extinction. Even when green returns, it may return differently. Ancient rainforests remind us that ecosystems can survive catastrophe, but the forest that comes back may belong to a changed world. The first grasslands came late, long after most dinosaur ecosystems ended. Grass feels so fundamental to modern landscapes that it is almost shocking to realize how late true grass-dominated ecosystems arrived. Most dinosaur worlds had no sweeping grasslands like the ones we know from later ages. Their large herbivores fed instead in forests, shrublands, fern-rich lowlands, and other plant communities built without the open grassy structure that now shapes so much of Earth. When grasslands finally expanded much later, they created a new kind of ecosystem with its own rules. Fire, grazing, fast regrowth, and open visibility began to matter in fresh ways. Running became more valuable. Teeth changed. Herding strategies evolved under broader skies. That lateness is what makes the story so fascinating. A whole major ecological stage we now take for granted simply was not there for most of deep time. The age of dinosaurs belonged largely to different landscapes. Grasslands were a later invention of the living world, and when they spread, they transformed terrestrial ecosystems into something strikingly new. Early whale ecosystems began in warm, shallow seas once walked by mammals. Whales did not begin as masters of the open ocean. Their story starts with mammals that could still walk on land, moving along coasts, rivers, and warm, shallow seas where food in the water offered powerful evolutionary temptation. Early forms retained limbs strong enough for life on shore, even as their bodies began adapting for swimming, hearing underwater, and feeding more effectively in marine settings. That transitional ecosystem is one of the most captivating in all of evolution. These animals were not trapped awkwardly between worlds. They were exploiting a rich edge where land and sea met. Shallows, estuaries, and coastal waters gave them room to experiment with a semi-aquatic life before later descendants became fully oceanic. The environment mattered deeply. Warm, shallow seas could feed, shelter, and challenge them all at once. From that setting came one of the greatest transformations in vertebrate history. The ancestors of whales first entered marine ecosystems, not as strangers from nowhere, but as land mammals, learning how to belong to water. Ice Age ecosystems paired mammoths, lions, and humans on the same plains. There is something almost unbelievable about the late Ice Age. once you picture who shared the same ground. On cold grasslands and open steppe, herds of mammoths moved across the horizon, while lions watched from cover and humans followed, hunted, scavenged, and adapted within the very same ecosystem. This was not mythic overlap invented later. It was ecological reality. People lived in landscapes where enormous herbivores shaped the vegetation, where top predators still commanded fear, and where survival depended on reading tracks, weather, and animal movement with great precision. The plains were rich, but never safe. A carcass might feed a family, attract wolves, and then draw larger cats before the day was done. What makes these ecosystems so gripping is the tension of coexistence. Humans were not outside nature, looking in. They were woven into the same food web as mammoths and lions, sharing one cold world of risk, opportunity, and astonishing living scale. Mammoth steppe ecosystems stretched wider than any modern grassland biome. The mammoth steppe was not a small regional habitat. It was one of the largest ecosystems Earth has known, stretching across immense parts of Eurasia and North America during colder phases of the Ice Age. This was a dry, cold, highly productive world of grasses, herbs, sedges, and open ground, maintained in part by climate and in part by the grazing and trampling of great herds. Mammoths, bison, horses, reindeer, and other large animals moved through it in numbers that modern landscapes can hardly match. What makes it so fascinating is that it does not have a true modern equivalent. Today we have tundra, prairie, and steppe, but the mammoth steppe combined traits in a way that now feels lost. It was vast, windswept, and crowded with large herbivores that helped keep the ecosystem open. To imagine it properly is to imagine a whole biome erased, an enormous living world that once dominated the north and then slipped away. Giant ground sloths helped shape ecosystems by browsing and trampling vegetation. Giant ground sloths were not just strange, oversized mammals wandering through prehistoric landscapes. They were major ecological forces. Some stood high enough to reach vegetation well above the feeding range of smaller herbivores, pulling down branches, stripping leaves, and opening plant cover as they moved. Their heavy bodies also trampled paths, disturbed soil, and altered the shape of the undergrowth in the places they frequented. In that sense, they may have played roles similar to those of large modern ecosystem engineers, though in their own slow and remarkable way. What makes them especially compelling is the contrast between appearance and influence. They seem almost dreamlike to us now, huge clawed mammals with a strange posture and deliberate gait, yet the marks they left on ancient ecosystems were practical and profound. By feeding, moving, and reshaping vegetation structure, they helped determine which plants thrived, which spaces stayed open, and how other animals used the same habitat around them. Ancient Australia hosted marsupial ecosystems unlike anything on other continents. For long stretches of time, Australia developed in relative isolation, and that isolation gave rise to ecosystems with a flavor entirely their own. Marsupials diversified into a remarkable range of roles, but elsewhere were often filled by placental mammals. There were browsing giants, swift runners, burrowers, climbers, and formidable predators, all built on a different evolutionary plan from the mammals dominating other continents. That is what makes ancient Australia so fascinating. It was not simply a familiar ecosystem with unusual animals swapped in. It was a world where evolution had solved the same ecological problems using very different lineages. The result was a continent of strange convergences and bold experiments. A predator might fill the role of a wolf without being one. A grazer might seem familiar at a distance, yet belong to a completely different branch of mammal history. Ancient Australia shows how geography can create a whole, alternate version of ecological possibility, complete, functional, and beautifully unlike anywhere else. South America long evolved isolated ecosystems with its own remarkable predators. Before stronger connections formed with North America, South America spent a long time as an evolutionary island continent, and that gave its ecosystems a wonderfully distinctive cast. Predatory roles were often filled by lineages that did not dominate elsewhere, including the famous terror birds and unusual mammalian hunters unlike anything in Eurasia or Africa. Herbivores, browsers, and smaller animals also followed their own evolutionary paths, producing communities that feel both familiar and startlingly separate. This is what makes ancient South America so compelling. It was a continent running a parallel ecological story with its own food webs, its own balance of power, and its own strange successes. Isolation did not make it ecologically poor. It made it distinctive. When continents remain apart, evolution gains room to improvise. South America did exactly that for millions of years. Its ecosystems remind us that there has never been just one way to build a predator community on Earth. Geography can write an entirely different script. Some fossil sites preserve an entire ecosystem after one sudden disaster. Most fossil records are assembled slowly, with bones, shells, and traces gathered across time. But some sites feel shockingly immediate because disaster struck all at once. A flood, ashfall, toxic event, storm surge, or sudden burial can capture many organisms from the same community in a narrow window, preserving an ecosystem in something close to real time. These sites are extraordinary because they hold more than isolated remains. They hold association. Plants, fish, insects, vertebrates, tracks, and even behavior can appear together in ways that reveal who shared the habitat when catastrophe arrived. That gives the fossil site a cinematic quality. You are not piecing together 1,000 scattered years. You are glimpsing one terrible moment that sealed a living world before it could disperse. The emotional power of that is hard to ignore. Disaster is tragic for the organisms caught in it, yet for us it sometimes becomes the reason an entire ecosystem survives as evidence, still gathered in one place. Volcanic ash can snapshot ecosystems almost like a buried photograph. Ash falls fast, settles widely, and can preserve a landscape with eerie precision when conditions are right. A volcanic eruption may blanket forests, lakeshores, floodplains, or wetlands in fine material that seals leaves, tracks, insects, and animal bodies before ordinary decay and weathering have time to scatter them. That is why ash deposits sometimes feel almost photographic. They record a surface rather than just isolated remains. A branch may lie where it fell. Footprints may remain sharp. Plants can be preserved with stunning detail, and whole communities may appear together under one sudden mineral shroud. What fascinates me most is the contrast between violence and preservation. The eruption itself is catastrophic, full of heat, choking particles, and rapid destruction. Yet the very force that devastates the ecosystem can also protect its evidence from time. In those moments, ash becomes an archivist. It buries the living world so quickly that the past survives not as a vague idea, but as something close to a scene. Oxygen-poor seafloors preserved soft-bodied ecosystems that usually vanished without trace. Soft-bodied life usually disappears almost completely after death. Without shells or bones, most organisms are lost to scavengers, decay, and current before they can fossilize. But when a seafloor becomes poor in oxygen, something remarkable can happen. Fewer scavengers disturb the remains, decay slows, and fine sediment can settle gently enough to preserve bodies that would normally vanish forever. That is why some of the most astonishing fossil sites on Earth come from ancient low-oxygen marine settings. There, jelly-like forms, delicate limbs, guts, impressions of skin, and other fragile details can survive with extraordinary clarity. These deposits change our view of ancient ecosystems because they reveal the hidden majority, the soft-bodied animals and subtle structures that normal fossilization almost always erases. Suddenly, the ecosystem becomes richer, stranger, and far more complete. Instead of seeing only the armored and the hard-shelled, we see the living softness that filled the sea. Oxygen-poor seafloors gave deep time some of its most generous moments of memory. Bone beds sometimes record drought-stricken ecosystems gathering around shrinking water. A bone bed can look at first like a simple pile of death, but sometimes it records a very specific ecological tragedy. In drought, water sources contract, and animals from across the surrounding landscape are drawn toward the same remaining pools, channels, or muddy basins. Herbivores crowd in first. Predators follow. Competition rises. Disease, weakness, and desperation spread through the population. If the water continues shrinking, the place can become a trap rather than a refuge. That is when bones begin to accumulate together. Such deposits are powerful because they capture a community under stress, not just random mortality. Different ages, species, and feeding roles may all appear in one place because the ecosystem itself was compressed by thirst. You can almost feel the pressure of the season inside the deposit. What had once been a broad living landscape has been forced into one crowded edge of survival. Bone beds like these remind us that ancient ecosystems were vulnerable not only to cosmic catastrophe, but to the slow cruelty of drying water. Tar pits preserve ecosystems by trapping both prey and predators together. Tar pits are among the strangest natural traps in the fossil record because they do not simply catch one unlucky animal. They can catch an entire chain of ecological reactions. A herbivore or small animal becomes stuck first, drawing attention through distress, movement, or scent. Scavengers and predators arrive to take advantage, then become trapped themselves. Over time, the deposit builds a community of victims linked by the food web. That is why tar pits are so rich and so revealing. They preserve not just abundance, but interaction. You see which predators were attracted, which prey were common, and which animals lived close enough to encounter the trap repeatedly. The surface may once have looked like harmless ground, yet beneath it waited a sticky death that turned ordinary ecological behavior against the animals involved. There is something chilling about that, but also scientifically brilliant. Tar pits turn predation, scavenging, and curiosity into fossil evidence, trapping whole relationships rather than isolated bodies alone. Ancient ecosystems were often built around microbes we almost never fossilize. When we picture lost worlds, we tend to imagine the visible stars of the ecosystem: towering trees, giant reptiles, mammoths, reefs, and predators with teeth. Yet many ancient ecosystems depended fundamentally on microbes that almost never fossilize clearly. These tiny organisms drove decomposition, nutrient cycling, soil chemistry, fermentation, and, in many aquatic settings, even the very base of food production. They were processing waste, breaking down dead tissue, feeding small consumers, and changing water and sediment chemistry in ways larger organisms relied on every day. That is what makes them so important and so mysterious. In many cases, the ecosystem we reconstruct from fossils is only the visible upper layer of a world held together from below by microbial labor. We rarely get to see those communities directly, yet their absence from the fossil record does not make them minor. Quite the opposite. They were often the hidden engine. Ancient ecosystems were not just built on bones and leaves. They were built on trillions of tiny lives doing essential work in silence. Lichens and mosses helped cloak rock and prepare ground for larger life. Before landscapes could support thick soils, forests, and complex terrestrial food webs, the bare surface of the land had to be softened and biologically altered. Lichens and mosses were among the quiet pioneers that helped do that work, clinging to rock, holding moisture, and beginning the slow breakdown of mineral surfaces. They created thin living covers where none had existed before. Their presence trapped dust, moderated temperature at the surface, and helped start the accumulation of organic matter. That process sounds humble, but it is foundational. A rock face or barren ground becomes a little more hospitable, then a little more, until larger plants and more complex communities can follow. What fascinates me is the patience of it. Ecosystem transformation does not always begin with giants. Sometimes it begins with a soft green film and a stubborn crust inching across stone. Lichens and mosses remind us that the preparation of land for richer life was not dramatic at first. It was slow, persistent, and world-changing. Nighttime ecosystems in deep time remain hidden, yet mammals once thrived there. The fossil record is better at preserving bodies than darkness, which means the night side of ancient ecosystems often slips away from us. We know a great deal about bones, tracks, and habitat, yet the actual feel of nocturnal life is harder to recover. Still, there are clues. Early mammals often carried traits associated with nighttime activity, such as keen hearing, sensitivity, and small body size suited to moving undercover when larger daytime rulers dominated the scene. That suggests vast ancient ecosystems had a second shift, one that came alive after sunset with different sounds, dangers, and opportunities. Insects would have changed their activity. Small hunters would have emerged. Scavengers and burrow dwellers may have relied on darkness for safety. What makes this so evocative is how incomplete it remains. We can sense the night world without fully seeing it. Ancient ecosystems were not only what happened in daylight, they also contained hidden hours where mammals and other small creatures built lives in shadow beneath the notice of giants. Some ancient ecosystems had no grass, no birdsong, and no flowering trees. One of the most powerful ways to feel the strangeness of ancient ecosystems is to notice what was missing. There were times when the land held forests, wetlands, and animal life of great richness, yet none of it included grass-covered plains, singing birds, or flowering trees in the modern sense. The sensory world would have been profoundly different. No meadow wind moving through blades of grass. No dawn chorus from branches. No blossoms filling a woodland with scent and color. Instead, there were spores, conifers, ferns, cycads, reptiles, arthropods, and later other sounds and plant textures unfamiliar to us. That absence matters because it breaks the illusion that ancient worlds were simply early drafts of our own. They were complete ecosystems in their own right, with their own atmosphere and emotional texture. When you strip away the sounds and plants we unconsciously expect, the past becomes more vivid. It reminds us that Earth has supported many fully functioning worlds that would feel immediately alive, yet deeply uncanny, to us. Evolution repeatedly rebuilt ecosystems after catastrophes with entirely new cast members. One of the most astonishing patterns in Earth history is that catastrophe does not merely damage ecosystems. It often clears space for replacement on a grand scale. After mass extinctions and major environmental upheavals, the ecosystems that return may perform familiar functions: herbivory, predation, decomposition, reef building, but with entirely different groups in the roles. That is what makes recovery so fascinating. It is not a simple restoration. It is recasting. A dominant plant group vanishes and another rises. A predator dynasty ends, and a new kind of hunter takes its place. Reef builders disappear, and different organisms learn the architecture of the sea anew. This repeated rebuilding gives Earth history a strange mix of continuity and reinvention. The ecosystem persists as an idea, but the actors change. That means the world can remain ecologically rich while becoming biologically unrecognizable. Over and over, life has rebuilt not by undoing disaster, but by writing a new script from survivors. The stage remains. The cast becomes something entirely new. The same place on Earth can host utterly different ecosystems across time. Stand in one place long enough, not for years, but for millions of years, and the transformation can become almost impossible to comprehend. A region that is now desert may once have been sea floor. A polar ice field may once have held forest and rivers. A mountain range may have risen from sediments laid down in shallow water crowded with marine life. This is one of the deepest wonders of ancient ecosystems. Place is stable to us because our lives are short, but in geological time, the same ground can host utterly different worlds. Climate shifts, continents move, sea levels rise, mountains lift, and life answers each new condition with a different community. That means the land beneath your feet has almost certainly lived many lives already. It may have belonged to reef, swamp, plain, woodland, or glacier long before becoming what it is now. The Earth is not just a changing planet in the abstract. Every location carries a long history of ecosystems layered one over another like buried worlds. Ancient ecosystems teach that climate and life always reshape one another. Climate shapes ecosystems in obvious ways, deciding where water falls, how warm the seasons run, and what kinds of life can thrive. But ancient ecosystems reveal something equally important in return. Life reshapes climate too. Forests pull carbon from the air. Plankton alter ocean chemistry. Wetlands store greenhouse gases differently from dry ground. Grazers can maintain open landscapes that burn differently from dense woodland. Again and again in deep time, the relationship runs both ways. The atmosphere and the living world are not separate stories. They are partners in a feedback loop that can amplify change, soften it, or redirect it entirely. That is one reason ancient ecosystems feel so relevant and so awe-inspiring. They show a planet in conversation with itself. Trees do not just respond to climate. They become part of it. Oceans do not simply host life. Their smallest inhabitants can help govern chemistry on a global scale. Earth history teaches that climate and life are always entangled, each shaping the future of the other. Every fossil site preserves only a fragment of an ecosystem, not all. Even the most spectacular fossil site is not the ecosystem itself. It is a filtered remnant shaped by burial, chemistry, scavenging, transport, and sheer luck. Hard parts preserve better than soft ones. Quiet waters keep different evidence than rivers. One season may be recorded, while another leaves nothing at all. That means every fossil deposit is both precious and incomplete. It reveals, but it also hides. This limitation is not disappointing. It is part of what makes paleontology so absorbing. Scientists are not reading a finished book. They are reconstructing a world from selected pages, weathered margins, and a few startling illustrations. A bone bed tells one kind of story. Pollen, footprints, coprolites, and lake mud tell others. Only by layering these fragments can we begin to approach the ecosystem that once existed. That process gives ancient worlds their haunting quality. We can see enough to know they were rich and connected, yet never enough to possess them fully. The past survives as invitation as much as evidence. Lost ecosystems were not primitive worlds, but fully connected living systems. It is easy to look at deep time and imagine crude beginnings, as though ancient ecosystems were rough drafts waiting to become modern. That picture is profoundly misleading. Lost ecosystems were complete living systems with predators, recyclers, food webs, competition, cooperation, disturbance, recovery, and countless fine-tuned relationships. They were not lesser because they lacked the species we know now. They were different, and often astonishingly sophisticated in how energy and interaction moved through them. A Devonian wetland, a Jurassic reef, or an Ice Age plain was not primitive to the organisms living there. It was home, dense with pressures and opportunities shaped by millions of years of evolution. This matters because it changes the emotional tone of the past. We are not looking back at half-made worlds. We are looking back at worlds that worked. They fed their inhabitants, challenged them, and sustained complex lives in their own terms. Ancient ecosystems deserve to be seen not as stepping stones, but as complete realities. Ancient ecosystems reveal Earth as a planet that keeps reinventing life. If there is one truth that echoes through the history of ecosystems, it is this: Earth never remains creatively still for long. Continents move, climates shift, seas advance and retreat. Extinctions tear through old orders, and again life responds by reorganizing itself into new patterns. Reefs return with new builders. Forests spread with new plants. Predators rise from unexpected lineages. Open habitats appear where none existed before. The continuity is real, but so is the reinvention. That is what makes ancient ecosystems feel almost inexhaustibly fascinating. They reveal a planet whose living surface is always in negotiation, always rebuilding, always surprising itself. The Earth does not simply preserve life. It experiments with it across time. Each vanished ecosystem is proof that the world has already been many worlds, each coherent, each beautiful, each temporary. When you look back across deep time, you are not seeing one long, static story. You are seeing a planet with the power to reinvent the living world again and again. As our journey through ancient ecosystems comes to a close, it's worth pausing for a moment and taking in just how many worlds this planet has already held. We wandered through forests that grew in Antarctica, through swampy lowlands filled with giant insects, through vanished reefs, inland seas, and cold open plains where mammoths, lions, and humans once shared the same bekal, horizon. We traced worlds built by microbes, by ferns, by conifers, by flowers, and by creatures so strange they can still feel almost unreal. And yet, each of those worlds was real. Each one lived, changed, and disappeared, leaving only fragments behind. A footprint in mud, a grain of pollen, a feather in amber, a riverbed turned to stone. The Earth has worn so many faces, and tonight we drifted among them, one by one, like lanterns glowing softly across deep time. Now, as the day fades further away, you can let all of it grow distant. Let the ancient forests dim. Let the old seas grow still. Let the footsteps, wings, currents, and rain of those lost worlds settle gently into silence. And if you've enjoyed this slow journey through the history of life, you might like to join me again in the next video waiting on your screen, if you happen to still be awake. And if these visits into science and wonder bring you peace, you can always like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, there is nothing more you need to do. Just rest. Let your breathing slow. Let your thoughts loosen and drift. And let the long memory of the Earth carry you softly into sleep. Sleep well, and good night.